All right, can people hear me? Anyone? All right, cool. So pretty much the format of this is we're just going to go over a few problems and or interactive problems, and it'll be fairly interactive in that we'll go over it, have some time to think about it, can share ideas in a Discord chat, and then go over the solutions. Also, yes, my brother made me give him the link in return for borrowing his Apple Pencil so he can listen to this. Anyway, to start off with, we're going to go over subtasks to Cave, which is in the Aurex set. So I'm just going to give you 2 or 3 minutes to read the problem if you haven't already, and then we're going to just go over the first 3 subtasks. So, yeah. As before, I'll be answering questions from Discord chat, so make sure to have that open if you have any questions. Have people read the problem? I can also just quickly explain what it's saying. Or do people want more time to read it? All right, I guess we'll just start discussing it. So for those who haven't read it, the question is essentially saying you have a graph. So you get given a graph. Somewhere I have my cheap drawing program. So essentially they give you a graph, and then you want each node has a robot at it. So we've got a graph. Let's number these nodes. So you have a graph 1, 2, 3, 4, like this, for example. Each node has a robot at it. You can do this several times. On each time, you assign either a 0 or a 1 to each edge. So for example, 0, 0, 1, 1. Then the second time, you can assign 1, 0, 0, 0. And after doing this some number of times, each node, which is its individual program, can only see the numbers assigned to the edges adjacent to it. And from there, it has to give itself a number such that every node has a unique number. Does anyone not understand what the question is asking, either from reading it or from me explaining it? I'll take that as a people know what the problem's asking. So we're going to look at the first 3 subtasks. The first one being, so the first subtask is t equals 8, t being the number of iterations of zeros you can have. And also the K forms a star. So we have then the graph looks like this. We have n take 1 here, and then every other node has an edge to n take 1. Yes, so then n take 1, 1, 2, 3, 4, n take 2. So we have this graph as our input, and we can send up to 8 iterations, t equals 8, and they're up to 256 nodes, n is up to 256. Does anyone have any ideas? So yeah, the idea said was basically just binary. So it's essentially that. So node n take 1 will know what node it is. The reason being it has n take 1 edges out of it. So from there, this node already knows what it is. Every other node will just have a single thing coming out of it. What can we do? Well, we can use the binary encoding. And so for each other node, for example, node 1, the different colors of this edge will just send 1 followed by like 6 zeros. For node 2, for the edge to 2, sorry. From the edge to 3, we can go, I've kind of written the binary encoding backwards, but for 4, we can go 0, 0, 1, etc. For 5, 1, 0, 1, it's backwards. But does that kind of make sense? So for each edge, we're essentially assigning a number from the 8 bits, and that number represents what node it points to. And then each node can just look at the 8 different bits it got, get the number from that, and then from there it has its answer. Does that make sense? Do people understand this subtask? I guess the point of this subtask is kind of an introduction to the problem. So if you don't understand what this subtask is doing, you're unlikely to understand the rest of the problem. So if you do have any questions, put them in the chat. That's it, everyone understands? I'm going to then move on to the second subtask, which is slightly different, I guess. T equals 8, the cave forms a cycle. That's fairly simple. You have node 1, node 2, node 3, node 4, node 5, back to node 1. Any ideas what to do in the cycle case? Well, I think they're 0 indexed, aren't they? That's my mistake. So it should be starting at node 0. So you have node 0, then node 1, then node 2, etc. My bad. 0, 1, 2, 3, back again. Any ideas on what to do for this subtask? And in this subtask, we still have 8 numbers we can assign to each edge. Any suggestions? Everyone's being very quiet. No one's got any ideas for this subtask? I'll give you a minute or so to think about it, and then we can share ideas. In the meantime. Oh, we have someone with ideas. That's good. Oh, not ideas. A story. No one have any ideas for this subtask? So the subtask is we have a cycle, and yeah. Do people want more time to think, or do you want me to go over the solution? I guess I will just explain the solution then. Everyone's being very quiet. Can people hear me? The stream isn't broken or anything, is it? I hope not. So in this case, we have the cycle. What we're going to do to each edge? Well, remember from before, we can essentially assign a number to each edge using our bits. We're just going to assign a 0 to this edge, a 1 to this edge, a 2 to this edge, a 3 to this edge, a 4 to this edge, and a 5 to this edge. And then each node then just says for each node in this case, except yes, each node can look at the two things on either side of it, and then just take the bigger one. So 1 would take this one, 2 would take this one, 3 would take this one, 4 would take this one, 5 would take this one, and then the node which sees 0 and n take 1 will then take 0, if that makes sense. I'm not sure if people are confused by the problem, so I think maybe I should go over implementing this to explain the solution. So I'm going to quickly go about implementing this subtask. It shouldn't take too long because everyone's kind of being quiet, so that's fun. So how I go about a two-step task is we have the code for our first person, Anita. This is the one which decides which edges to be lit up. And then the second code from the robot has to return the number. Everyone's being very quiet. This is uncomfortable. Trying to remember how the... yes. So how we implement this problem, because I didn't go over the sample implementation, you may have not read that. So the code for Anita, what it does is it has to give t vectors essentially. Each one stores which edges are lit up in each iteration. And then the second code, the robot's code, then gets essentially this vector for each, gets a vector for each adjacent node when they're lit up, and then has to output a number. Okay, how do we implement this? I did not prepare for this, so this will be fun. We're doing the cycle case. So then the ith edge connects nodes I and I take 1. And so we're just going to give the ith edge number I. Okay. We can go over each bit. And then for each edge. And so then the question is, how do we check whether the number j has the ith bit set? So what we're doing is for each bit, if this number has that bit set to 1, light it up. And to do that, we can use bitwise operations. We can say, so if j and 1 I, this says, this is bitwise shift to the left. So this turns 1 into 1 becomes i's, if I equals 4, it becomes 4 zeros and then 1, if that makes sense. So then it just multiplies by 2 to the power of I. So then if j and 1 are I, it says if the ith bit is set in j, then and then I should have read, we're going to light up these tunnels. Okay, does everyone understand what the kneader code is doing? It is just going over each bit individually, and then it's saying for all the numbers, all the edges that have this bit set, light them up, and then do that. Does that make sense? Okay, time to do the robots. Well then, what do they get? They get a vector of strings for the tunnels. The string being like, I believe, something like that. If it's not set for the first bit, set for the second one, set for the third one, not set for the fourth one. Okay, how to do this? Okay. D being the number of adjacent edges for each adjacent edge. Oh, the sample code does it for you. That's convenient. So the ith edge is lit up at each time. So we're gonna store the values of our edges, and we're gonna say okay, so what is this code doing? Wrong value. We're saying for each of our adjacent edges, which will be 2, D will be 2, we set a value to 0. For each bit, if it's lit up, then we set this bit to be true in the number. So this operation says bit shift 1 j across, so to the power of j, and then set that bit to true in val, and then push it on the edge. And then what we're doing is decide what identifier is. What we said was, we said before, somewhere, we said we have 0, 1, 2, 3, 4. We said we take the biggest value, so each number will return the biggest one out of the two it sees, with the exception of the one which sees 0 and take 1. In that case, it will return the smaller one. For convenience, let's just sort this array of size 2. So in the case where we node 0, we just return 0. Otherwise, we just return the biggest one. Does that make sense? Hopefully this code works. Let's have a look. So how do we compile modules? Sometimes you'll get stuck with this, so I'm going to go over it again, even though I think it was in the doc and the problem statement probably says it as well. But to compile modules, all we need to do is just put the two source files there, and then it will compile it. Oops, there are some issues. Unused parameters, whatever. Let's make an input file to test it. What is the input format on this problem? Where is it? Here. Okay, first value should just be 0. Second line is n, which is, we'll say 5, and take 1, which is edges 4, and t, which is 8. And then we just saw the edges. 0, 1, 1, 2, 2, 3, 3, 4, 4, 0. There are 5 edges. Let's just, and our code has an issue somewhere. It's assigning numbers 0 to the first one, 1, 2, 3, and then it's assigning 0 to the last one. Okay. Shame. Let's just debug this. Let's just print what the edge values are. Uh-oh, that's an issue. What's going on? Have I given the input insane? Oh, that's my mistake. Input's broken. Thanks. Okay. So I fixed the code, but it's still broken in that it's going 0, 1, 2, 3, 3. What's our issue? Oh, there's something wrong here. Did this sort not work? No, it did. Okay. What's the issue? You should return the max sufficient. Zero, 1. What's the issue? So in this case, n is 5. Why is it getting 0, 3? Have I done? Is the input still insane? I know what the issue is. The issue is that we're only assigning values to n take one of the edges. We're not assigning values to all the edges. Okay. Now it works. So the bug was I was only considering n take 1 edges rather than n edges, which means the final edge was being ignored. So no edge was getting number 4, it was just getting number 1. And now it works. Time to submit and hope it works. And we got AC. Nice. All the subtitles we're going for. Nice. I think I'm going to move on to another problem now after getting that subtask. Okay. So new problem time. We're going to go over... xylophone. I'm going to send a link to the problem statement in the Discord. And then we'll have some time to read it and think about it. So I'll give you 10 minutes until 2:45 Sydney time to have a look at the problem and read it and think about it. Then we'll go back and hopefully be a bit more interactive. I'll just find a problem statement. 1 second. Alright, I've sent a link to the problem in the Discord chat. We're going to have 10 minutes to read the problem and then think about it, and then we'll share ideas. another 5 or so minutes to read it and think about it. If anyone has any questions, just post me in the Discord chat. Give another minute or two, and then we'll share ideas and discuss. Okay, does everyone understand what the question is asking, first of all? Any questions about that? Everyone has read it in the past 10 or so minutes? I'll take silence to yes. Does anyone have any ideas for subtasks or for full solution or anything? So subtasks are subtask 1 ends up to 100, 2 up to 1,000, 3 up to 5,000, and we can use 10,000 queries in all subtasks. What's your idea? Feel free to share your idea. Okay, so the idea that just been said was, we start by, where's this? We start by, we query the entire range, and then we query the entire range minus 1, then the entire range minus 2, until this value changes. And in this case, that means that must be the lowest or highest value. The reason being, so to give an example, we have 1, 3, 4, 2, 5. Yes, so we start by querying the entire range, and then we query just this, and notice we get a different answer, because here, first query we'll get the answer of 4, and next query we'll get the answer of 3, and so we know this is the maximum value. So once you found the and then we do the same thing on the other side. We can then walk this one in until this value changes, and this gives us, so we now have the highest and the lowest value. From there, what can we do? I think a different example of that idea was, let's say we have 1, 5, 2, 4, 3. We query this, we get 4. 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 We query this, we get 0. So now we know that this one's the biggest instead of what we're previously querying. We know this one's the biggest, and then do the same thing on this side. We'll get this one's the smallest. So now we have a way to find the biggest and the smallest. We don't necessarily know which one's which, but we do know one of the two is the biggest and one of the two is the smallest. Because we don't have the guarantee necessarily that the biggest occurs after the smallest. We could have, for example, this is valid input, 2, 5, 1, 3, 4. We would find, going from the left would find this one, going from the right would find this one, sorry, going from the left would find this one here. And so we don't know which one's biggest, which one's smallest, but we do know. Oh, sorry, I misread that guarantee in the problem statement. Thanks for pointing that out. I thought it meant something else. So sorry, we have the guarantee that the bar of the lowest pitch is smaller than the bar of the highest pitch, which means that, sorry, we know that the biggest one, if we walk in from the right, we get the biggest one. Walk in from the left, we get the smallest one. That's my bad. I thought it meant the first thing has a smaller value than the last one. Okay. So now we have a way of finding the biggest one and the smallest value. Does anyone have any ideas of how I can go from there? Another question, how many queries do we use in the worst case to find the biggest and the smallest value using this method here? Yeah, so we use n queries, even though we're walking from the right and from the left. Notice that these walks will never overlap. So therefore, we're going to use n queries in the worst case. Okay, now we have the biggest and the smallest in n queries. Maybe we can do it better, but maybe just doing subtasks. Once we have that, does anyone know how we can then find other values? Feel free to share your idea. The method to get everything inside the biggest and smallest in 2 queries each. Show the idea. Otherwise, I have an idea that we can use once we've done this. Several people are typing. That's good. So we've had another idea that's been said, and that is, what if we start by querying I9 plus 1 and then I9 plus 2? So let's say we constantly query I and I plus 1. What does this give? That gives us a difference between adjacent elements. And so, for example, we have 5, 3, 1, 4, 2. We will get from these queries 2, 2, 3, 2. This is actually insane input, isn't it? Because we have to swap these two. We now have 1, 3, 5, 4, 2, and we get a slightly different output, but there we go. And then the second query we're going to do is going to query I and I plus 2. So we're going to query these two. We're going to get 4. We're going to query these two. We're going to get 1. We're going to query these two. We're going to get 3. And then what we're going to do with this information? Well, so this first query essentially just tells us the difference between JSON elements. So if we kind of graph the points, we can go, well, we have a point here. We're either going to go to this one. We're either going to go down to or up to. We're then either going to go kind of down to again or up to again, or down to again or up to again. And then like from there, we're going to do something else. But now consider our second query. Our second query from 1 to 5. This gives us 4. Let's put this in two cases. The first case is we either go down twice or up twice. The second case being we either go down up or up down. So in the case where we go down twice, the difference between the first and the third element is just the sum of these two differences here, because we went down both times. Or if we went up both times, the sum of the difference between first and third is also 4. However, if we went up then down, or down then up, then we have the guarantee that actually this number is not going to be equal to these two added together, because we've gone opposite directions. In that case, the result's going to be the difference between these two. And so now we can tell, using these two queries, what can we say? We can say the difference between these two elements, and we can tell whether we either went up, up, or whether we went down, down. Or whether up, down, down, or whether we went like this. So how can we use this to find the answer? I think people have pretty much just worked it out. What we can do is, the second query, the query of the form I plus 2, tells us whether the parity of whether it's positive or negative, the difference positive or negative is the same or different for both of them. So for example, we now know whether either both the first two differences are both greater than 0 or both less than 0, or they swap. So using this, we can then, let's just assume that the first jump from 1 to 2 is positive, it goes up. From there, can we find the answer? Well, based on the query from 1 to 3, we know whether this goes up or whether this goes down. Let's say it goes down. Based on the query from 2 to 4, we know whether this goes up or down. So then we say it goes down, etc. So we can then work out all the values, assuming this first jump was up. So now we have kind of two options. Either the first one was up or have the mirror of this. How do we work out what one's which? Well, we have the guaranteed the biggest element occurs after the smallest element, and only one of these will have that constraint, the other one will be the opposite. And so we're just going to get the answer from there. The second point is, well, this tells us the difference between values, not the actual values, but we know that every value is between 1 and n. So if we just follow this, find the smallest it gets to, that's 1, and then kind of move everything up or down the corresponding amount, such that that's the smallest one, if that makes sense. So does everyone understand that solution? Are there any questions about that? And then one question from me is, how many queries does it use? You may have discussed that earlier, but it was discussed. So in the worst case, it uses n take 1 plus n take 2, or not worst case, it always uses that many queries, which is 2n take 3, which is less than 10,000. So this goes straight to the full solution. Does everyone understand that? I might briefly discuss subtasks as was suggested, because there are some subtasks. And we've just gone straight to the full solution. But does everyone understand that? Okay. So subtask 1 is n is up to 100. Intention is use n squared queries. How can we do this? Well, let's expand the idea from before. Let's start by finding the biggest value. So we walk in from the end until we find the biggest value. And then we can just kind of recurse on both sides and just keep walking until we find the second biggest value. Or then we can just keep kind of walking in this way until we find the biggest value on this side of it. And we can keep walking this way until we find the second biggest value on this side of it. And then kind of repeat this process. And so, I believe something like this will work for n squared queries. I haven't thought about it in great detail. And then to get this to subtask 2, 10,000, intention is n log n queries. And we can just apply binary search to an idea like this in order to use in order to use n log n queries. That's not the fair point. In subtask 1, you can query every single range. And so once you know that, you can apply some method to find the answer. But does everyone understand the solution to that problem? And it's kind of nice. The solution is simple in the sense that the queries done are fairly simple. The implementation is going to be fairly simple. You just have to do the 2 loops of queries and then some adjusting based on where the minimum value is and if the biggest one occurs before the smallest one, etc. But I think it's not necessarily worth discussing too much what to do when we have every range. I think because we have solved the full solution, maybe we should move on. We're gonna do a similar thing to before. We're gonna present a problem. We're gonna have 10 or so minutes to think about it or have a break. So the problem will be cup. I will send a link to this problem when I find it. And we're gonna have until 20 past to read the problem and think about it, and then we'll be back. For those who don't know what XOR is, I'll quickly go over it because it's relevant to this problem. If we have the bitwise representation of each number, so we have for example 5 and 9. If we get the binary representations of both of these numbers, we have for 5 1 0 1. For 9 we have 1 0 0 1. Bitwise XOR says go bit by bit, and if both bits are the same, you put a 0, and if both bits are different, you put a 1. That's the XOR of two numbers. It's called XOR because it's exclusive OR. It's like, is this one true? Is this one or this one 1, but not both of them? That's XOR. Anyway, 10 minutes, think about this task and read it. Link in the Discord. another few minutes. One more minute. Okay, time to discuss the problem. So, a very quick rundown of what it's asking us. You have a grid where you have a grid from negative billion to positive billion, and inside of that you have a smaller grid of the billion by billion from negative 500,000 to positive 500,000. And there is some hidden point inside this middle rectangle. For example, it could be here. You guess a point, and it tells you the XOR of the absolute difference in X. So this value difference in X, XOR difference in Y. Fairly simple, and using this you have to find this mystery point in as little queries as possible. For full, 32 queries, but there are partial marks available. Okay. We essentially have a solution presented here. I'll take a read of it. Anyone else can share their ideas as well. Okay, we essentially have a solution given there. I guess I'll just go over it. That was kind of fast. So the idea is we're going to start by querying some point somewhere, let's say top corner of the grid, and that gives us the XOR of the x distance and the y distance. The x distance and the y distance. Let's say we only change the x coordinate of this point. Then every query after that is like the x distance XOR a constant because we're not changing the y. And so we essentially have a query which is now we get the distance in like the difference in x, absolute value of that, XOR some constant. That is essentially the query we have. And so then XOR some constant. And so then from there, how do we use this query? Well, the idea that was presented in the chat was just to consider it one bit at a time. So let's say we're considering the ith bit. We're going to then query, let's call this old coordinate xy. Now let's query x plus 2 to the I, y. What does this do? Well, let's consider if in this old distance here, in the old x, if the ith bit was set. Well, if the ith bit was set, then the new distance, the smaller x, is just this old distance, so old x minus 2 to the power of I. Why? Because if the ith bit is set, we've now, by moving forward this way 2 to the power of I, we've essentially unset that bit, and so our new distance is just the old x without this bit being set. Okay. Then consider how that would change our how that would change the XOR we get here. Well, consider two cases. Consider the case where this bit was set and we've now unset it. Well, the only bit that changes in this number is the ith bit, and nothing changes in this number, which means the ith bit would change in the answer to our query. Let's consider the second option. The second option is, well, what if this bit wasn't set in this old distance? Well, then in our new distance, so we have kind of, let me just erase this. We had the old x distance, we have like the initial x we're querying and the actual x. So the old distance here, we now have a distance along here of 2 to the power of I. We now have this new distance here. Well, this number is going to look different to just the old distance without the ith bit being set. It's 2 to the power of I. Why? Well, if it just looks like the old value without the ith bit set, well, that would mean that the ith bit was set in this old value here, if we're moving closer. Second case is, well, what if actually we got further away from the x coordinate, and so then the ith bit went from being unset to being set? Well, in that case, the actual value must be to this side by 2 to the power of, must be 2 to the power of I to this side, in which case it would be at this s coordinate, I believe. That's the second case. To kind of prove the idea that in the case where the ith bit wasn't set in the old distance, that other bits must change. Essentially to prove I'm being corrected. What is... I'm being. So you go to top right. So another idea is being presented in the Discord chat, and that is essentially we're always going to move upwards. So we're going to have our box here. We're going to start by querying this top corner here, and then to check each bit, we're going to jump up to the power of I. And so that idea essentially says that in the old distance, if the ith bit wasn't set, once we move up to the power of I, the ith bit will be set. Now consider the case where the ith bit used to be set. So let's say the distance was this, for example. We're checking if this bit was set. If we move up, we're essentially adding this number to it. So plus this. In this case, if the ith bit was set, our new number will involve some other future bit being changed because of the fact that we add these two together and it kind of moves along to this one. But if this was 0, then only this bit would be changed. So then to check like one bit, to check if each bit is set, so we first jump up 1 and we say if the result of the new query is not just the old query but with the first bit changed, then we know that the initial bit was a 1, otherwise it was 0. Then we move up 2 and we say if the result of our query wasn't just the old query but with this bit changed, then there must be a 1 there, otherwise there's a 0 there. Then we query this bit and we say, well, if the new distance by jumping up that far is just the old distance but only this bit changed, then this distance had a 0 there. After doing that log n times, we now know this distance, we know each bit of this distance, we know this distance, and then we just XOR it with this value to get this distance here. The issue of that solution, I believe the only issue is that the size of this outside box doesn't allow you to do the final distance, if that makes sense. I think the method that I used, which is very similar, kind of all the ideas are very similar, but the method I had in mind was we're initially just going to query the point just outside the box here. So we're going to query like just one outside this box here. And then we're going to do the bit solution. So we're going to go, okay, just move x across 1. So move x across 1 to here. And then consider two cases. Consider the case where the old distance had this bit set in it. So for example, the old distance was this number here, which had this bit set. The new distance is going to be this minus this equals this. And notice because of how XOR works, if only one bit changes in this number and this number stays the same, then only one bit will change in the query result, and so our query result will differ by only one bit. Okay, consider the second case where this wasn't set. Well, there's two options. Option 1 is the answer lies on this side of us. In that case, we have a number like and we're subtracting like 0, 0, 0, 0, 1, 0. In that case, from how subtraction works, we're going to see that this bit here is going to change in our answer, and so in that case, we're going to see not just this bit change. That's the first case where this bit wasn't set moving this way. The second case is, well, what if we jumped forward like to the power of I this way, but the actual correct location is between us? Well then, can we show that, well, no other bits will change? Well, yes. Consider the case where the old distance was this, and we want to show that if we jump our query past it, then this new x distance here is not just this number, but without this bit being set. And how do we show that? We'll consider what this would look like. This number without this set is just the old distance minus 2 to the power of the ith bit. And what that would look like is the old distance is here. The old distance is this minus the ith bit. We're looking at the distance being we have back this way. Oh yes, okay, so we're proving that this distance here is not equal to this distance here with this bit removed. Well, we know that these distances added together must add up to 2 to the power of I, because that's how far we jump this way. And like this distance plus this distance must equal 2 to the power of I. And so consider like the old distance plus this new distance cannot equal 2 to the power of I unless the original distance was 0. Because, 1 second, sorry. Had the proof before, sorry. Okay, yes, and so we have 2 to the power of I is greater than this old distance x here because we jumped past it. And want to prove that this is not equal to 2 to the power of I take x. Well, if they add together to get 2 to the power of I, we then have this one is just the inverse of this plus 1. And if it's the inverse of this plus 1, in that case, it's not going to be just this number with this bit, with the ith bit changed, because the other bits, the bits below here would have changed, and hence that's not the case. Does that kind of make sense? The proof is kind of dodgy. But it's the same idea that Kwong presented, but we're querying from here and going this way rather than going that way. I feel like you also need to investigate an important property of XOR, which I think we skipped over, and that is that A XOR X XOR X equals A. Essentially that XOR undoes itself. The simple kind of proof of that is, well, let's say we have A and we have X, which can be anything, and we have X again. X XOR X is just 0 because these bits cancel out, and so then we then result in just A XOR 0. And then I guess you need to prove other features of XOR. But I guess the generalized version of XOR is just either an odd number of bits or either an even number of bits. And you can show that XOR has the required properties that this is true. The people understand a solution, I feel like it got a bit confusing in there. But the idea is we binary search on X, we find the X distance, and then from there we find the Y distance. Does that make sense? Or does anyone else have a simpler way of explaining it? We have a thumbs up. Anyone else? I'm free to answer questions. Or if anyone has other solution ideas, whether they be the same or suboptimal, happy to discuss them as well. We have 2 yeses. Anyone else? I'll look at your solution. I hadn't read it. So I think we can discuss the second solution which was presented because it's quite different. And so then let's do two queries. We're going to do a query with some A, Z, and then we're going to query A take 1 and Z. So what are these results? These give us X, the X being the original, the actual, so that's the answer being X and Y, X comma Y. We get X minus A, XOR X minus Z. And here we get X minus A take 1, or X minus A plus 1, I guess. Do you want us to be a plus in here then? XOR X take Z. We actually these two result together. These cancel out because they're 0, and we get X minus A XOR X minus A plus 1. If we have these two results, you're essentially XORing a number by 1 less than that number, assuming you're outside the... So assuming we create outside the box, and so we got closer, we're XORing a number with 1 less than that number. And in that case, you get like XOR for example. And so when you XOR a number with 1 less than number, it gives you all the how many bits until the first, gives you a number of bits until the first until the least significant bit. So I guess the property of XOR is, let's consider what happens when we XOR a number with 1 minus itself. So we have like some number with some zeros at the end. If you subtract 1 from that number, you get like these numbers stay the same, except this last one becomes a 0, and these all become 1s, which means if we XOR like some number B and B take 1, that essentially tells us what the least significant bit in B was based on the result, because the result is going to be 0, 0, 0, 0, 1, 1, 1, 1, and that gives us the least significant bit in this number. So in that case, you have the least significant bit in the X distance, and then the solution was, well, then we'll change our number to this new number. So then we can now subtract this bit from our distance. We can then move up, in this case by 8. We can go plus 8. The new distance will be like these mystery bits here, and then all zeros because we've got rid of the least significant bit. We can repeat the same process of querying distance and like 1 plus a distance, and we'll get the newest least significant bit, and we keep doing this until we have our X distance. And once we have our X distance, we can then XOR that with our original result, which gives us the Y distance, and we get our answer. So that's the second solution. Does that one make sense as well? I hadn't thought of that solution yet, so that's quite a nice one. If not, there's any questions, we're going to move on to one final problem. And I don't have a problem statement for it. It's one which some of you may have heard before. hats or hets. Is everyone ready for me to move on to the final problem? So the problem was originally posed by Ronald at 2016 April. Ronald is a New Zealand person, so he originally said it, I guess. And so the problem is there are N people all wearing hats. I will say the rest in not an accent. So that you have N people who each have a hat, and so they're each wearing a hat. So you have N people in a circle, numbered from, let's say, 0 to n take 1. So n equals 5. You have 0, 1, 2, 3, 4. Each of them is wearing a hat, and let me just quickly recall the problem. Okay, yes. So everyone has a number on their hat, not necessarily unique. So everyone has a number in the hat, they don't know what that number is. So for example, this person would have the number 32200. You have the guarantee that every number on the hat is an integer between 0 and n take 1. So no one has a number negative number or a number bigger than n take 1 on their hat. So everyone has these numbers on their hat, and everyone can see everyone else's hats other than their own. And so the question is, every person writes down on a piece of paper what they think the number on their hat is, and if one person or more gets it correct, they all win. So to say that again, there are n people in a circle. N people in a circle, n equals 6 in this case. Each of them wearing a hat. Each hat has a not necessarily unique number from 0. So they each have number AI on their hat. Between 0 and n take 1, not necessarily unique. So they could all have 1, for example. This one has 2. They all make a guess as to what number's on their head. They can't hear other people's guesses. And if at least one person gets their guess correct, they all win. Okay, any questions about the problem? If not, we'll have a 5-minute break to think about it. They cannot see other people's guesses, so they will write down their guesses secretly. Otherwise, if you could see other people's guesses, they could just say the person next to them had. And so everyone makes a guess secretly, and then that's what happens. Does everyone understand what the problem's asking? So just to say again, to answer some questions. So you can think about it as a task where you have to write n programs. Each of them is given the numbers on everyone else's hat. They can discuss beforehand. So they can discuss beforehand their strategy before they know the hats, and also each person kind of knows who they are, if that makes sense. So like, two people know different people, I guess, in the sense that like, you can think about each instance of the program is given what person they are and all the other hats, if that makes sense, rather than not knowing what person you are. And yes, you want a strategy that works every time. So I guess if you have some high probability strategies other than just guess randomly, that might be interesting. But I think guess randomly has a fairly high but not high enough probability of success. Anyway, I'll give you 2 more minutes to think about it. Yeah, but each person knows who they are. You can think about that as you could assign each person an index, and each person knows their index. Or in terms of a real life problem, each person can get together, they can get there beforehand, and each individual person can have their own strategy, if that makes sense. So like, let's say 3 of us are playing. Each of the individual 3 people could have a different method they use to find their answer, so long as between them, one of them is correct. If you're interested in a subtask, one subtask is n is a power of 2. So I guess here's some subtasks. I thought subtask 1 point, because this is JY, n equals 2. Subtask 2, $30 points. No, 40 points. It's getting a lot of points. 40 points. N is a power of 2. Subtask 3, no further constraints. Okay, we can start discussing. Does anyone have any ideas for any of them, including the n equals 2 subtask? I think it's not necessarily worth just dismissing that. Maybe we can think about what can we do with n equals 2? Is there some strategy we can use? So for n equals 2, let's just consider every case. So n equals 2. We have person 0 and person 1. The cases are 0, 0, 0, 1, 1, 0, 1, 1. So there are kind of 4 cases for n equals 2. Do we have some strategy that could result in one person always guessing correct? Any ideas? Okay. Yeah, so the idea I was suggesting in the chat was, well, there are essentially 2 options. Option 1 is both values are the same. Option 2 is the values are different. So let's say person 0 assumes they're the same, and person 1 assumes they're different. So then person 0 guesses the same as the other person, and person 1 guesses differently. You're guaranteed that exactly one of them will be correct, because either they have the same number or they have different numbers. This is, I guess, an example of what I said earlier of each person knows who they are. In this case, person 0 and person 1 use different strategies, but together you're guaranteed that one of them will be correct. So does everyone understand the n equals 2 solution? All right. So I guess now we know n equals 2 solution. Does anyone have any ideas for anything else? Any observations for any other, maybe n equals 3 or the power of 2 subtask or full? Doesn't have to be any solutions, just any ideas. Bits. So one idea was maybe, so in the case where we have n is a power of 2, that was one of the subtasks, so n equals, let's say 2 to the power of k for some k. That maybe hints at us, because sometimes subtasks do kind of give hints in a way. This is hinting that maybe for this subtask we might want to consider the binary representation, because otherwise what does kind of a power of 2 have any meaning outside of that? So let's say, are there any ideas of how we could use the binary representation, or maybe use XOR, which was suggested? I'm gonna give a minute to think about that. So could we somehow use XOR, I guess? And maybe think about the n equals 2 subtask where there were two options, either the same or either different. In this kind of more general case, there are a lot more cases, but can we somehow limit it to, say, n cases and then use that? Because in the first instance, n equals 2 had 2 cases, and each person assumes one of those 2 cases. If we have n cases, each person can assume one of the n different cases, and then we can somehow use that to find the answer, if that makes sense. Interesting. So the idea that was suggested was everyone outputs their index XOR the XOR sum of everyone else's hats. That seems like an interesting idea, and I guess out of nowhere it seemed kind of random, I guess. But let's kind of investigate that. So the idea was the XOR sum. What that meant was like just XOR everyone else's hats together. Consider the overall XOR sum of, we'll call it the XOR sum. The XOR sum of all n hats. What are the options for this XOR sum? What values could it have? Do we have any bounds on the XOR sum of the n hats? That is, when you XOR them all together. it must be between 0 and n take 1. Why? Because each person's hat has a value between 0 and n take 1. We know n is a power of 2. So for example, if n equals in binary this, then everyone's hats use only these first 4 bits here, which means the XOR of them can only use these bits. So yes, in general, when n is not a power of 2, this doesn't hold, but if n is a power of 2, the XOR sum of all the hats is between 0 and n take 1, because only these bits here can be set, which means only these can be set in the XOR. So for example, we have 4 people on their hats, so n equals 4. On their hats, let's say there are 0, 0, 1, 1, 1, 1, 0, 1. The XOR sum of all these hats would be 1 here. So generalization of XOR is if there's an odd number of bits, you set to 1. If there's an even, set to 0. So the XOR sum is 1. Okay. So how can we use this idea that there are n different possible values of the XOR sum? Anyone have ideas of how we can use this? There are n people and n possible XOR sum values. So let's look at the strategy. What if person 0 assumed the XOR sum of the n hats was 0, person 1 assumed the XOR sum of the hats was 1, person 2 assumed the XOR sum was 2, etc. Up to person n take 1, who assumes the XOR sum is n take 1. Let's say, okay, person I, they know the XOR sum of everyone else's hat is some value a. If they think the overall XOR sum is I, what possible values could their hat take? Well, because of how XOR works, we know that if the mystery value x, if we know that like x XOR a equals I, then if we XOR both sides by a, we get x XOR a equals I XOR a. These cancel out. We get the value on their hat must be equal to their index XOR the XOR sum of everyone else's hats. Or I kind of say that again. So person I will assume the overall XOR sum of everyone's hats is I. So everyone's hats, including theirs, XOR together gets I. So and so then using that, they'll guess their own hat by saying, well, I know the value on my hat x, XOR everyone else's hats put together equals I. Therefore, my hat equals my index I XOR everyone else's hats put together. Does that make sense? Maybe if you're unfamiliar with XOR, it kind of might seem weird at first. But if you think about the properties of XOR, that is going to be true. And so this is the same solution I presented a while ago, which was just your index XOR sum of everyone else's hats. However, I guess in this case, it kind of proves why that works. So to kind of prove why this works overall, person I gets their hat, assuming the XOR sum is I. Okay. This means that exactly one person will be correct, the person which correctly guesses the total XOR sum of everyone else's hats. So before we move on to full solution, does everyone understand why this works for n is the power of 2? Because we know the XOR sum must be between 0 and n take 1. And so from there, we have our answer. Any questions? give you another 10 or so seconds to, if you don't understand, I'm free to go over it again because, again, it might seem like some Excel magic, but hopefully, if no one else mentions it, I'm going to assume everyone understands it. Okay, moving on to full solution. So why doesn't this work for full? Well, we needed to know that the XOR sum was between 0, the actual XOR sum, and n take 1. Why? Because each person assumed the XOR sum was their index, which means most of the actual XOR sum must be between here. However, consider the case where n equals, for example, 3. It is possible in that case, n equals 3. So people were numbered 0, 1, and 2. So the XOR sum I claimed could have a value of 0, 1, 2, or 3. Why? Let's consider the cases. We have like 3 people, each with a number between 0 and 3. We could have between 0 and 2, sorry. We could have, for example, 2 and 1. The XOR is 3. We could have 2, 1, 2, 1, 0. We could have all 3 people have 0. XOR sum is 0. We could have one person has 1. Everyone else has 0. XOR sum is 0. One person has 2. Everyone else has 0. XOR sum is 0. So here we have 4 possible XOR sum values, but only 3 people, which means that if everyone assumed what the XOR sum was, it's possible that then no one guessed correctly, and so no one guesses their hat correctly, if that makes sense. So I'm going to mistake there. I meant to have 2 instead of 0. But you see in this case, there are 4 possible values and 3 hats. Okay. So in this case, we use the XOR sum, which doesn't work when n is in a power of 2. What's another property instead of XOR sum that we could use to try and find the answer? Some property that, some other sum of all the values, for example, that isn't the XOR sum. Okay, idea was the sum modulo n. Okay. So our new sum we're defining is just the sum of everyone else's hats, or the sum of everyone's hats, modulo n. Okay. The sum of everyone else's hats modulo n, is that an integer between 0 and n take 1? Yes, because of how modulo works. So we know that the sum of everyone's hats modulo n is between 0 and n take 1. Okay. Let's say person I assumes that the modulo sum of everyone else's hats is I. So let's say they add everyone else's hats together and they get some number A. And they say, well, I want to equal I. What could my thing get? So we get kind of like A plus X equals I, or A plus X kind of equals I mod n. So then we kind of get, I should rub out. We then get, by some, I guess, just addition, we get the mystery, their value equals, X equals their index minus the sum of everyone else's. But then we're not using actual sum, we're using sum mod n. Does this guarantee a unique answer? Well, yes, because we know that both these values are between 0 and n take 1. If you subtract them and then get the answer modulo n, you're guaranteed a number between 0 and n take 1 as well. So kind of 2 cases. Case 1 is I is greater than a. This case, this number is, we know this number is going to be greater than 0 or greater than equal to 0 and less than n, which means that that's valid mod n. Case 2 is I is less than a, this number is negative. However, to get the negative number modulo n, you just kind of add n to kind of undo one of the modulos, and that'll get a number between 0 and n take 1, which is x. And so we're guaranteed that this is a unique number modulo n, because both of these, between 0 and n take 1, and it will work. And so if person I assumes the sum mod n is I, then they get a unique number for their hat. If everyone assumes that it's a different number, the sum is a different number modulo n, so person 0 assumes it's 0, person 1 assumes it's 1, person 2 assumes it's 2, exactly one of them will be correct, and so exactly one of them will get the correct answer. Does that solution make sense to everyone? It's very similar to our subtask solution, except we haven't used XOR sum, we've just used the actual sum. Any questions about that problem? Yeah, I think the idea of the XOR seems silly now. I had that same thought when I solved this problem originally, because again, I got presented the same subtask, and I guess you see 2 to the power of n, you think XOR, and you get to the solution. But then when the actual solution is just like, you add them all together, it seems a lot simpler, I guess, than the subtask solution. But the thing about a lot of interactive problems, which is nice, often the solution is very simple, but not easy to come up with. So once you know it, it's like, this is just so easy, how did I not come up with this before? But to actually get there can take some time, because it can be very simple, but hard to come up with, I guess. Okay, that's all I had planned for this lecture. I guess anyone's free to ask questions about that problem or any other problem. Otherwise, we'll just finish up. Oh, question about kth number. Yes, that problem last time I checked was broken. I'm not aware of it ever working. I guess have a look at that now, and I can fix kth number, because that's been broken since its existence, I think. A fun fact about kth number. So it was originally at 2017 April, it was put on ORAC. Someone got turns out whatever solution they used to get the answer was broken, but then, was it Albert? Was it Albert or was it, Anand? Either Albert or Anand submitted and got AC, and they were like, well, someone's got AC, therefore 2 solutions get the correct answer, it must be right. As it turns out, in big cases, the answer is output a bunch of zeros, but for whatever reason, both people's solutions had the same bug, and so the bugged solution got AC because its bug was the same. For people who don't know what kth number is, it's not a problem in the interactive set, it's a problem in, I'm guessing, a data structure set you have. But yes, it's broken for now, but I will fix it. Any other questions? I'm going to cover output only. I didn't have any output only tasks to go over, but I'm happy to discuss them in general, or one in particular if you want me to. But I didn't have any in mind to cover. Do people want me to go briefly over output only tasks, if that's just how to do them, or do they want me to go over a specific example of one in the set? That's true. So I guess something. So emergency from Fario this year wasn't an output only task, but it kind of was in the sense that like it was essentially an output only task, except instead of submitting output, you submitted your code, but you got the input files. The reason for that was just so that I guess for people who hadn't done output only tasks before, it was more comfortable. And that was the reason for that. But you can treat it as an output only task essentially. You can play with the input on your computer, and then at least on CMS, you could actually hard code the answer and submit it. Because of ORAC submission limits and because of ORAC scoring not adding up, it's quite difficult probably to hard code all of them. I don't actually know the ORAC submission limit and whether that's possible, but it might be. What's your ORAC submission limit? 40 kilobytes. But any other questions? Do people want to go over anything else? Otherwise, I guess you're free to go now. Alright, I guess 10 more seconds or so to ask any more questions. Otherwise, I will stop the stream. Faro debrief. I could do a trial exam 1 debrief now. I haven't actually read the problems. And so that would be... But if people want to go over... Is there any specific problem from trial exam 1 people want me to go over? And for people who don't want trial exam 1 debrief, you're free to leave, I guess. But is there one problem? Citizens. Any other problem? Because I haven't actually read Citizens in a while. Or Citizenship. I believe I remember the general gist of the solution. This is the right one. Yes, I think so. So I guess we'll go over citizenship now. This is a problem session for all of us because I can't remember the solution. Let me read it. Essentially, you essentially need to pick some country to go to, and I guess you have some order, and you order them in such a way that it's always optimal to the optimal ordering, I guess. Oh, how great. My solution is just a segtree bash. That's annoying. So I guess for this problem, let's say we chose the countries we're going to visit. We also need some ordering of these countries that's optimal. And so I guess the hard part of this problem is, what is an optimal ordering of the countries? And so the idea presented was ordered by the minimum of P and Q. Is this optimal? Well, let's see. So let's say we have two countries, P1, so countries with, we have countries with P1, Q1, and P2, Q2. We want to prove that if you have an ordering of countries where you visit both P1 and P2, you want to visit P1 before you visit P2, if that makes sense. Where we have min P1, Q1 is less than min P2, Q2. Is this the claim you're making? I'm kind of doing this on the fly. How do we prove this? Well, you lose citizenship to a country if you don't go there for this number of years. Okay, so look at it this way. Every time we fly between two countries, like let's say we're flying between, we visited like some number of countries. We visited like country 1, country 2, country 4, country 3, and country 1. And now we're going from country 1 to country 8, for example. In this case, we can fly by, I believe this works, right? We can fly by every country we formerly went to, so that we don't use citizenship to those countries. Is that how it works? I believe that's how it works. So you can fly back and visit all of these countries on your way to visiting country 8. So then the condition for not losing citizenship to this country is just that every country we visit after it. Oh, I did not go over to here. Okay, I'm really sorry. I've been drawing, but you can't see my drawing. So let's say we visited country 1, 2, 3, and 4. We go from country 4 to country 5. The condition for not losing citizenship to country 3, because when we go here, we're going to bypass all these countries on the way. The condition for not losing any of these is just that our stay at 4 was not greater than the time to lose these ones. So we had the condition that Qi is less than Pj for I is less than j. Yes, so this needs to be true in order for us to not lose them. And if we lose this, might well not visit that in the first place. And so the condition we want is that this holds. Okay. Let's then order them by minimum of these values. So then we want to show that this is not suboptimal. So let's say, consider the case where we ordered them by this ordering, and then we had it such that, well, actually, this is bad because Q2 is greater than, P2, the time we spent at 2 is greater than Q1, meaning that because we visited 2 after 1, we lost our citizenship to country Q1. We want to prove that if this is true, then the other ordering just wouldn't work. Okay, if we have Q1 is less than Q1 is less than P2, then we also have Before we jump in, I'm just kind of doing this on the fly. We also have that, so we have min P1 Q1 is less than or equal to min P2 Q2. And so we have do we want to order them by reverse this? Is this what we want to do? Or descending, my bad. So we want to order them the other way around. So we want min P to Q to be greater than or equal to this. So then we have so let's say we order them in this ordering. Then I gotta show the outline of this proof. So this is what sometimes is referred to either by exchange argument or kind of proof by bubble sort. What we're going to show is in some optimal ordering of countries that we have some way of defining for some country I that it should be before some country J. And how do we prove this? We prove this by going, if they were adjacent and it was JI, we could swap it such that the ordering went like IJ instead, and it wouldn't be any less optimal. If we can prove this, then by bubble sort, we can prove that by sorting by this priority, so we assign some priority AI to them. If we can prove that like, if we have some JI where AJ is greater than AI, we can prove that in that case, if we swap I and J, the ordering still works. By bubble sort, if we sort all the values by AI, then that optimal ordering works, if that makes sense. So kind of people understand how the general idea works. This proof by bubble sort. So then the claim was that we can sort them by the minimum of PI and QI. And so to prove that, we're going to say, well, assume that we have the breaking condition. The breaking condition, which is that QI is greater than PJ, which meant that we lost our citizenship to this country Q because is less than, sorry, which means that we lost our when we visited country J, we lost our citizenship to the country I because this condition was true. This is the condition that needs to be true in order to lose it. If this is true, however, because we know that this value is bigger than this value, then in that case, we must have the case where PI must be, we must have PI is less than QI. Why? Well, because we know that the minimum value is greater. Sorry. So if this is true, how we know the minimum of these two values is greater than the minimum of these two values, which must mean that PI here is smaller than QJ here, QI here. Is that sufficient? That must be the case. And it must also be the case. Okay, I've worked out the proof. Okay. So it took me a little while. Okay, so we have the case that QI is less than PJ, meaning that in this ordering, we're going to lose citizenship to country Q when we go to country P. However, we have the case that minimum this is greater than the minimum of this, which means that okay, the suggestion was I draw a PQ plane. I keep forgetting which one's which. So if we had the condition that QI is less than PJ, how does drawing work? let's say we drew the first, this is point I here. Qi, Pi. We know that Qi is less than Pj. What does it look like on this plane? Right, this value here, well, are you able to draw out your plane interpretation and send it here? And then otherwise I can just continue with what I was doing before. So we have that Qi is less than Pj. However, because the minimum of this is greater than the minimum of this, then we must have the case where the minimum value here must be Qj. Why? Because the minimum of this is less than the minimum of this, which means we must have Qj is less than Qi and is also less than Pi. So we have less than or equal to. However, because P's and Q's can't be equal because one's odd, one's even, we're not strict lesson. So we then know that Pi is greater than Qj, which meant that if we swap the order Ji, we would have the case such that Qj is less than Pi, which means what we've shown here is that in the case where we order them by minimum P and Q, if some I and J doesn't work, if we were to swap their ordering, it still wouldn't work, which means that in every other case, ordering by this is optimal. Does that proof make sense? If we can visualize it, I don't know what you meant by visualizing it, but if we can visualize it, it might make more sense. But essentially the argument is, can do a proof by contradiction. Consider the case where it fails, which is this case here. By doing some thinking, because of this condition up here, we know that Qj must be less than this because of the less than condition. It must also be less than Pi, which means that if we swap them around, we get Qi less than Pi. Qj is less than Pi, which proves that if we ordered them country J then country I, we would lose our citizenship to country I when we went to J when we went to country I. Does that, if people are still watching, is anyone still watching who wants to know the solution to this problem? And if you are, did that proof make sense, or do you want me to go over the diagram? And if you're not watching, I might just stop, because is anyone watching? That made sense. Okay. So then, if we order the countries by this, we now know the optimal order to visit them, or not. Just do have some questions about it. So I can try working through this diagram. It's just that, sorry, I didn't prepare for this in advance. So conflicting area for points above P equals Q. So yes, we haven't done so the first part of the solution is we sort them by this priority here. We sort them by decreasing order of the minimum of the two values here. And once we have the optimal order, and the question is, how do we actually solve the problem? So then the claim is that it's just a greedy. I haven't thought a lot about this second part. So let me think about it for a second. So the condition we have as before is that each QI must be, for it to work, we must have this is true. So we then have some number of countries. I want to pick the maximum set of countries, I guess, such that this condition holds. How do we do this? Well, can we greedily do it? What was the greedy? I guess another way we can do it is by a DP, I believe. The DP solution is just like, wait, does that work? I might take that back. So the greedy idea was take all countries where PI is less than QI. And for all countries, I'm going to take ones that don't conflict with any country before. Did you have a proof? Did you have a proof for that? For the greedy? Or people who solved it, how did you prove it? Sorry that I hadn't prepared this in advance. Just waiting for you to finish typing. This is a proof for the greedy part. If it conflicts with country above the P equals Q line, then might as well take the country instead. Okay. So let's just draw the PQ. PQ. We plot each point. We've sorted the countries by a minimum P of P and Q. And so I guess the min PQ line is like this. Because this will hit ones with the maximum minimum value first. Yes? Yeah. Wait, no? No, it's like a... It's not diagonal, it's like a... this. And so, imagine this line sweeping down. This line here represents the minimum of P and Q, because if minimum P of Q is Q, then it's going to be here. If minimum P and Q is P, it's going to be here. This is sweeping down to the origin. This is what it means to sort by minimum P and Q. And then the greedy idea was take all countries where PI is less than QI, so take all countries that lie on this side of the line. Does this work? Are we guaranteed that if we take countries up here, that they will never conflict? The conflicting condition being the reason is no two countries above this line will never conflict. Why? Because both of these countries have Q as their minimum value, so that the smallest value for all these countries is their Q, which means that their P is bigger than their Q, and so they're sorted in decreasing order by their Q values, and because their P is smaller than their Q, the minimum value in this case is their P, and so we know that for all these values, they're sorted by their P value, and their P value is less than their Q value, which means this condition will always hold. So again, all countries above this diagonal line, the minimum of their P and Q is their P, which means all these countries here are sorted by just their P value. And we want to say that for each one, in decreasing order, that for this point here, its Q value is bigger than this one's P value, where we know this one's P value is bigger than this one's P value, and this one's Q value is and then this one's Q value must be this one's P value is smaller, which means this one's Q value must also be smaller because confusing myself. Alright, sorry, this doesn't mean what to prove, but we want to prove that for all points above the line, if we take them in this order, they'll always work. Why is this? Well, if they're above the line, we have the condition that for that one, Pi is less than Qi. That's the condition being above the line. We also have that if we visit this one before this one, we have the case that Pj, the one we visited afterwards, is less than Pi. This means that Pj is less than Qi, which is a condition that we can take them in that order. That's something wild proof, but does that make sense? Which means that for 2 points above this line, we can just take all of them. And the claim was then for points below the line, For points below the borderline, only take them if they don't conflict with any countries before. So then, if we then visit a country here, we only want to take it if its value isn't, if its value QI PI, sorry, if the time you stay there for isn't bigger than any other countries beforehand. Do you want to know the proof for that? Otherwise, I'll try and come up with it. Sorry, it's taking a while. As you can probably tell, I have not read this problem for years. So I'm just trying to formalize the proof. Anyone has it. Also, no obligation to listen now. This is kind of just me trying to prove this problem. If my thinking is correct, so we have PQ, we have some point here. It conflicts with everything before it, where its p-value, pi, is greater than their q-value. So its p-value is this. If their p-value is greater than its q-value, that means that it kind of conflicts with everything that lies if it's greater than, it conflicts with everything that lies below here. No, that can't be right. Is it above? All right, so yeah, so this point here, it conflicts with everything below this line, but only stuff visited. So this is our sweep line, so it only conflicts with like these points here. Okay, the claim was we might as well take these points here instead of these points. So case one is we might as well take this one here instead of this one here. The reason being, I guess in all cases, it's fairly easy as to why we want to take these values instead of this one. Because of the fact that in all these cases, their Q value is larger. And if their Q value is larger, then they're less likely to conflict with something later on. So if this point here conflicts with something beforehand, we might as well take the thing beforehand because of the fact that its Q value is larger. I think, is that proof valid? Okay, that is me done with that problem. I don't think I'll solve any other problem because that took me a while given I hadn't prepared for it. Okay. Any other questions? Otherwise I'm going to end the stream. Okay, bye.